Hello everybody, my name is Nathalie Gontier and I'm going to be giving the closing talk of this colloquium on networks and evolution organized by Eric and Philippe. And I want to start by saying thank you very much to Eric and Philippe for having invited me to participate in this very interesting colloquium. I'm a philosopher of science, and one of the things that I'm interested in is the history and philosophy of scientific thinking, and where within that history we can find the rise of network thinking and what that network thinking stands for. So if you look into the history of philosophical and scientific thought, you can distinguish between different cosmologies. So you have the cosmologies of the ancient Greeks, the Judeo-Christians, classical physics and natural history with the rise of science. And then today we have modern physics and modern evolutionary biology. And it is within this modern physics and modern evolutionary biology that you find the rise of network thinking. And that network thinking already in evolutionary biology, for example, dissociates from thinking about evolution and about living organisms in terms of trees of life. But so this transition from trees to networks that we find within evolutionary biology is itself something that can be placed into a broader history where we can distinguish between these shifts in cosmologies and also these shifts in cosmographies in how the basic ideas of these cosmologies are being depicted in these iconic images. And so here we can distinguish between transitions going from wheels of time and change of being to scales of nature and timelines, timelines and trees to networks. And so we're going to be looking into some of these examples of where we can find this transition from tree to network thinking, in which sciences we can find them. And one of the most important sciences where we find this transition is evolutionary biology. So Darwin was one of the first to implement tree thinking into evolutionary biology. And in his notebooks and in one of his notebooks and also in The Origin of Species, he drew these hypothetical trees of life, and these were then immediately implemented in the field of anthropology by his good friend Ernst Haeckel, and also in linguistics by August Schleicher, who would draw trees of the Indo-European language family. So not only the evolution of biological organisms or of the human species, but also of languages was something that would become depicted into trees. But today, these trees of life are being criticized because they are unable to depict any kind of horizontal merger. And so if you look into reticulate evolution, which is evolution that occurs by means of symbiogenesis, hybridization, lateral gene transfer, or in general the study of infectious diseases, what people do there is they investigate how different species or how different lineages on a tree of life interact with one another. And so what you get then is these networks. And also in linguistics, we see the shift from trees to networks to depict certain aspects of language evolution. Also in anthropology and cultural evolution studies, we see the implementation of network thinking. And I found it very interesting that if you go to the website of the Cultural Evolution Society on the web page where they are going to define what cultural evolution is, the first image that you see there is a network. And that, of course, contrasts greatly with the images that we are used to think about when we think about human evolution. So on the top, for example, we see this caricature, but this is in many ways how anthropology has been defined. It has been defined according to the idea that there is some kind of linear progress, going from chimpanzees to Australopithecus, to Homo habilis, Homo erectus, the rise of agriculture, the Industrial Revolution, and then the Technological Revolution. In many ways, cultural evolution has been conceptualized as something that progresses linearly in time and that you can somehow have a straight line evolution. While today, these ideas of straight line evolution are being countered, and one way to counter them again is by implementing network thinking. And also in ecology, we see the introduction of network thinking. One example is that there is a transition going on from classical food chains to food webs. So in a food web, again, you have nonlinear interactions between multiple organisms that are being depicted in a network-like structure. And these are a new way to depict and to understand the food chain, which goes back to the idea of the existence of a chain of being. And also in philosophical thinking, there is the introduction of network thinking, especially when we think about what knowledge is. So before, knowledge used to be understood as a very linear relationship that occurs between the human being and the outer world. While today we understand knowledge as something that is present in different organisms and they also interact with one another. And so if we want to investigate how these organisms interact intelligibly with each other and with a possible outer world, then there too we find the introduction of network thinking. And if you're interested in these images and more examples than the ones that are given, beyond the people that are participating in this colloquium, I could also very warmly recommend you to have a look into the website of David Morrison, The Genealogical World of Phylogenetic Networks, where you can find many more images, not only of trees but also of networks. And I also made a special issue on how these images define biological but also cultural and linguistic evolution. So what is going on? Why do we have these transitions and what do they imply? We're going to analyze these questions from within a field that I call applied evolutionary epistemology. And so on the one hand, we're going to ask how do these networks underlie the formulation of a new worldview? How do they differ from existing worldviews and how do they help define a new worldview? Which is a question that asks about the evolution of epistemology. So if we look into how humans have evolved their knowledge, what do these networks imply about the evolution of human knowledge? And on the other hand, we're also going to ask ourselves the questions, how do these networks help to define the structure of evolution? And that is something that relates to the study of the epistemology of evolution. So what we know about evolution as a phenomenon in the world. So we will begin by focusing on this first question. How do networks underlie the formulation of a new worldview in the history of science? So as I said, we can distinguish between different cosmologies within the history of Western thinking, and these cosmologies each associate with different cosmographies, and these cosmographies are these diagrams, these important images that associate with these different worldviews. So for the ancient Greeks, for example, the most iconic diagrams or cosmographies of their time were wheels of time and chains of being. And these are replaced by Judeo-Christian worldviews where scholars introduce the images of a scale of nature and chronologies and pedigrees. And classical physics introduces timelines and phylogenetic trees, and modern physics and evolutionary biology associates with the rise of this network thinking. And one of the things that my work has demonstrated is that there is a significant correlation between these shifts in these diagrams and in these worldviews in general, and how these worldviews define time. And then, secondly, that there is a significant correlation between the changes in how these cosmologies conceptualize time and how they understand causality. So the ancient Greeks had a circular notion of time. So one of the things that they were very interested in was the motion of the planets, for example, around their geocentric Earth. And another thing that they were very interested in was seasonality. So spring, for example, is followed by summer, summer is followed by autumn, autumn is followed by winter, and this is something that reoccurs the next year. So one of the things that the Greeks were very much involved in was this kind of timekeeping, and for them time was something that was circular because there was always a return of the planets to its original position, or there was the return of the seasons each year anew. So for them, there was some kind of circular notion of time, and we also find that in their ideas, in the way that they understand cosmology and their cosmography. So time was depicted as a wheel, and here also we have the idea that there is a chain of being, and causality wise, for example, there is also the cyclicity that is and the circularity that can be found there. Aristotle, for example, said that there is this cycle, this recurring cycle of coming and becoming. So what is alive must die, but then also what is dead will come to existence again. So there was some kind of a notion of reincarnation there, in what regards the existence of matter. Now, if you look at the Judeo-Christian worldview, and this is something that starts from the Romans onwards, this circular notion of time is changed for a linear notion of time, because according to the Judeo-Christian worldview, the world has been created, and therefore time has also been created. So the universe then and the world at that time is understood as something that has a beginning and an ending in time. And so time in that regard becomes understood as something that is linear. And this linearity is also found in their cosmographies. We see that in their scales of nature that are understood as stairs or ladders that go from less to more perfect, for example. And it is also here that we see the introduction of numerical time, or the beginning of numerical time, that then finalizes with the rise of the sciences. So, for example, in classical physics and natural history, it is here that we see the introduction of time understood as a decimal number line, going from 1, 2, 3, 4, 5. But it is also here that we see the introduction of phylogenetic trees, and what we find here is that this linearity that was introduced by Judeo-Christian traditions is being replaced by multilinearity, the idea that one species can give rise to species A, but also can give rise to another species B. And so what do these networks then depict? Well, I think that these networks associate with the notion of space-time. And so I think that there is a way that these networks are attempting to introduce the concept of space-time as it is being introduced in classical physics, and that is what these networks are trying to capture. But so we will be looking into that for the remainder of this talk, with what it is that I mean by that. So, for example, if you look at the left image here, what we see is the paleontological tree of the vertebrates, which was introduced by Ernst Haeckel in his book, The Evolution of Man. And so it's very interesting to see this image, which is a tree of life image, and the different ways there are to think about time. So first of all, on the tree itself, we see a distinction made between different ages. And ages are, of course, periods in time. So we have the age of the invertebrates, the age of fishes, the age of reptiles, and the age of mammals, and the age of men. And what is interesting is, though it is talking about these ages, is that there is no mention made anywhere of a numerical timeline. Instead, what we see is that this tree of life is set in the geological time scale. And so we see on the left the Archaeozoic, Paleozoic, Mesozoic, Cenozoic, etc. And so what is interesting about this image is that it has no uniformity. The geological time scale has no uniformity. And so we see that these different time periods and also these different ages, some of them last longer than others, so there is no uniformity. On the other hand, if you look at the middle image, if you look at the Cartesian coordinate system, wherein today these trees are set, we find a numerical timeline, and that timeline is uniform. 1 stands at an equal distance of 2, and 2 stands at an equal distance of 3, as 2 stands to 1. So what we see here is a more uniform way of thinking about time that associates with the introduction of a numerical timeline. And so how we conceptualize time there associates also with the transformation from catastrophic thinking to uniformitarian thinking, which is something that we can find in evolutionary biology. And so time becomes understood as a linear succession of events of matter in motion, and causation then becomes understood as a linear and timely relation between cause and effect. A causes B, for example. And also, if you look into the different developmental cycles that we see, this is also something that can then become put upon a linear timeline. So if you look into the development of organisms, the ancient Greeks, they would think about development as something that is cyclic. And then these cycles would later become understood as periods and as ages. So a different way of thinking about ages is about the age of a baby, the age of a toddler, the age of a teenager, for example. And so what you find is these different developmental phases. And these different developmental phases over the history, within the history of evolutionary thinking, have also become straightened, because now that is something that is measured by time. So you are a baby from 0 to 2 years old, for example, and from 2 to 4 years old, you're a toddler, etc. And so trees of life, phylogenetic trees of life, are most of the time they are set into a Cartesian coordinate system where they are tracking how matter changes over time and in space. And so here you have this linearity or this multilinearity when you investigate how one species diversifies into many species. But one of the things that you have, because it is being set into a Cartesian coordinate system, is that you have to have a consistency in time. You study how A diversifies into B and you follow that trajectory. And that is one of the reasons why trees are so able in demonstrating vertical descent and in demonstrating the past and the history of a certain species. But when you look into networks, they do not depict that kind of phylogenetic descent over time. Instead, they study horizontal interactions, and one of the things that happens there is that most of the time networks do not depict time at all. So time disappears and there is no tracking in a Cartesian coordinate system, but instead there is some kind of multidimensional scaling, and then that is non-linear and there is no necessity to be consistent with time. And we find that especially in ecology, reticulate evolution, and also in ontogeny. And I think that is a form of investigating what I call the extended present. So what do I mean by that? To better understand what I mean by that, we have to look into the epistemology of evolution, and we have to investigate how these networks help us to redefine the structure of evolution. If you look into the neo-Darwinian synthesis, according to them, the structure of evolution is as follows. You have the unit of evolution, and that is the organism, that evolves at the level of the environment and that evolves by means of natural selection, which is the mechanism of evolution. So you have a causal account that is mechanical. And if you look at that in the middle column from within a hierarchy, you have the idea that genes bring forth organisms and organisms bring forth species. So you have the distinction there between micro, meso, and macro evolution. And if you look upon that from within causality, that hierarchy, if you examine how that hierarchy examines causality, then the idea is that genes bring forth organisms and that organisms bring forth species. So that is a form of upward causation, which is depicted by the black arrows on the left. Now, the whole discussion about the extended evolutionary synthesis is whether or not there is such a thing as downward causation, whether a species can influence how an organism evolves or whether an organism influences how genes evolve. But one of the things that these hierarchies again do not depict in any way is any kind of reticulate evolution. So symbiosis, symbiogenesis, lateral gene transfer, mobile genetic elements, hybridization, etc. is not depicted in these linear hierarchies. And if you look into what is being called the extended evolutionary synthesis, there also, the way that it was defined by Pigliucci and Muller, there also you do not find any mention of reticulate evolution and any mention of network thinking, because they were very much thinking from within these hierarchical structures and thinking in terms of up and downward causation. Now, one of the things that I think that reticulate evolution is demonstrating with these networks is that we are breaking free from these classic ways in which we have been thinking about causality and in which we have been thinking about evolutionary hierarchies. So if you look at something like reticulate evolution, like, for example, how the microbiome interacts with an organism and how different organisms live in symbiosis with each other as a form of parasitism or mutualism or whatever. One of the things that is being done there is that people do not look into evolution from within this rigid hierarchy of how a gene brings forth an organism and brings forth a species over time. Instead, they investigate how genes from one species and an organism belonging to another species together bring forth this new individual, and then bring forth something like a holobiont. And if you look at that, then what you get is the investigation not only of upward and downward causation, but how you can skip certain strands of a hierarchy. How can a gene go to a certain species? How can a gene from one species go to another species? And how these different strands sometimes combine into what can be characterized as a new hierarchy, because you have a gene of one species and a gene of another species together combining into yet another species. And as such, what I think that these networks are introducing is it is a new way of conceptualizing hierarchy and causality theories. And we find that most of all in association with reticulate evolution studies. And what I think there is that what is being introduced is an interactional hierarchy, or what I call an interactional hierarchy, and that differs from the classic embedded and linear hierarchies. So in pre-evolutionary thinking, the causality was understood as something that was linear, going from the inorganic to the organic to the superorganic. With the rise of the modern synthesis, that hierarchy is evolutionized, and so that goes from genes to organisms to species that form an embedded or a nested hierarchy. And with the extended synthesis, beyond thinking about that hierarchy in terms of upward causation, you have the notion of downward causation. So the idea that species can influence how organisms evolve and organisms can influence how genes evolve. Now that idea not only associates with the extended synthesis, it also associates with Donald Campbell, who actually introduced the concept of downward causation and introduced it in psychological and in cognitive thinking. And it was also through him that it was applied in sociocultural thinking. But so what we see today with these forms of reticulate evolution and also studies of ontogeny and ecology is that we have an investigation not only of upward and downward causation, but an investigation between different units and levels, and those are studied without assuming any kind of upward or downward causation, and without assuming any kind of directionality in time. What we are interested in is interactions. For example, today, if we want to see how the human species is transporting the COVID-19 virus, for example, across the globe, it is not of relevance where we come from and how we evolved when we want to depict how in our current present, in our extended present, this virus is conquering the world and is conquering our species. What we need to study is interactions. We need to study how we humans travel. We need to study how we humans infect one another during our lifetime, how children infect their grandparents, how grandparents infect perfect strangers that then infect or reinfect grandchildren, etc. So that is something that goes beyond the classic linear thinking and beyond up and downward causation. And it are these forms of interactions that underlie these new forms of hierarchy and causality thinking that I think that are being introduced by networks. And what such a view implies is that we recognize the plurality of different units, levels, mechanisms, and processes of evolution, and especially the plurality of hierarchies. And that to me is what applied evolutionary epistemology is about. It is about finding what these units, levels, and mechanisms of evolution are and how they together bring forth not one but multiple ontological hierarchies. And so to conclude, I think that this transition from trees to networks is part of a scientific revolution, an ongoing scientific revolution, One that is demonstrating and that is associating with the introduction of the notion of space-time into evolutionary sciences. So no longer are we interested in only studying how things evolved over the course of natural history. We're also interested in studying, for example, how a virus conquers the world in no time in the extended present. So we want to know how organisms interact. We want to know how reticulate evolution, symbiosis, symbiogenesis occurs, and that is something that occurs in the ecology of nature. That is not something that is something that only occurs in the past. And so the outlook is different. And what we need then is the development of hierarchy and causality theories that take these forms of reticulation into account. And so we need reticulate hierarchy and causality theories. And so that, I think, is the challenge of the future. And so I want to thank you all very kindly, and thanks again to Eric and Philippe for this wonderful symposium. And here are some of my publications and also my website and my contact details, which you can find on the top of this slide. Thank you.